Hello, hello everyone. Okay, guys, we will start. I hope you can see my screen and also you can hear my voice. If so, just let me know. Okay, sounds good. Thank you. Before I start this lecture, so I would like to hear something from you guys. So how is the course in general? Do you like it? You were expecting something like this, or you were expecting something is a fancy machine learning? If you have anything in your mind, just write it there, and I will be reading it before we start the lecture. Also, we need to wait a few more minutes. Slightly too much math, which is great. Okay. Didn't expect as much math. Okay. Seems more math heavy than I hoped. Lots of math. Yeah, that's actually a good point. Like so far, but need more practice. Some questions, numericals. Look a bit more complex than expected. Lab is interesting but challenging. The math theory is still confusing to me, but okay, if anything is confusing, just join my office hour. It's like from Thursday, 3 to 4, sorry, 4 to 5, and I will be able to help. I mean, this is the basic machine learning which I was expecting. Yeah. Okay, so today we will have another day of heavy math, and I don't want to say sorry about that, but this is how it is that right? This is not like a machine learning for engineers. It's not like a machine learning course. It's kind of a mix between deep math and also machine learning things. So we might have only one or two problems of heavy math, then we will be kind of slightly off with those kind of stuff, but we will be using the results. We will be using the results to do regression, classification, clustering, back propagation, forward propagation. A lot of things will be relying on this. That's the reason why we need to understand the math and the linear algebra. How this advanced viewing to align with machine learning? Yeah, so that's a good question. Yes. So it aligns with machine learning because most of the stuff that we are doing here is kind of studying the math. So we will be able to formulate a cost function or a regression model function or perceptron like criterion function. This will be related to here. And also last lecture and today's lecture is about one kind of classifier, which is the Bayesian decision theory. That's one kind of classifier. And so far we haven't actually talked about multi-class classification. It's only two classes, omega 1 and omega 2. This is what we deal with. But from next lecture we will actually generalize this to multi-class classification, and we want to deal, and we will know how to deal with that. The other thing is we talked only about linear regression, not linear regression, linear discriminant functions, where we have linear things, but we haven't talked about the general case of discriminant function, which is, it could be like quadratic, polynomial, whatever. So about someone is hints about questions for the midterm and finals. Okay, so for questions about the midterm, I have posted some practice problems for you guys. Please go over that and try to solve it yourself. And if you did that, then this means actually this is a good sign for me that you understand kind of this kind of math, and you will be able to do well in the midterm. Try yourself, and I will upload the solution next week, the whole solution. Okay, so what else? Okay, so I think we are good now. Let's start the lecture. Yeah, for the term project, the guidelines for the term project, I think I already like posted one file. Please, usually you have to look at my model is called administrative documents. If anything is related to labs, anything related to submissions, term project, please look at that. Will the midterm be in person? Yes, the midterm will be in person. It will be like same lecture time in Engineering 103. It's 2 hours. I will announce about that, but yes, it will be in person. Problem set is coding. So it's not like in the midterm, you will not have anything related to coding. that thing of the practice problem set 1, I just give you like part of it is math. You can do it by yourself, by hands. And the other thing is coding, which I already posted the code for you guys. It's just to give you some understanding on how changing the learning rate will actually affect your local minimum. But there will be no coding question in the midterm or the final. It's all solving problems for undergrad students, and we might have some different questions for graduate students. Okay, I think I have addressed most of those things. Okay, the date for the midterm is February 26th. It's the week after the reading week. It's the week after the break. Okay, so if there are more questions, we can answer that during the break. But let's start the lecture now. Yeah, so for today, I will go a little bit slower. Okay, I will go a little bit slower with today's, but in general, it's kind of straightforward. If you follow me, don't write after me. If you like to write, you can write, but don't lie, because I usually like upload my complete and clean notes. We'll have 3 midterms on the same day. So usually what we do is we submit our proposed date for the midterm, and then the department will actually say if there is a conflict or if there is no conflict. Since I haven't received anything from the department, means there is no conflict on that date. But if there is more than 3 midterms in the same day and the department found that there is a conflict, then they will actually inform me that to change the date. But I haven't received anything, means we are good with the exam for the midterm time and the date. Okay, so last time, what did we talk about is we talked about one classifier is called the Bayesian decision theory, which is one type of classifiers, but the simple thing with this classifier is that everything is given to us. Is that right? And today's lecture is from chapter 3 of your reference book, if you want to read from that. But there it's very abstract, and I don't know if you will get a lot of information from there. I have expanded a lot of things here in my notes, which is very comprehensive. So back to the bias rule that we have is we studied this kind of bias rule last time, and we found that everything is given to us. Is that right? So we have a data set. And from the data set, we can calculate the prior. B of omega I, this is called the prior probability of class omega I, which is given. For example, if you have 60%, you have 40%, they will say BWI is 0.6 or 0.4. And the other thing is this, which is the likelihood. The likelihood is actually the probability density function of the feature X given omega I, given omega 1 or given omega 2. So for example, if you have a feature which is a nose or ears, how that feature between 10 and 12 is dense for class 1 more than dense for class 2. This is how we can read the likelihood function. Again, this likelihood function is also given to us, is that right? When we dealt with this one last time with one feature, we actually formulated and we also model it as normal distribution. But in fact, this can be normal distribution, but it can be like estimated. And there are many estimation methods to estimate this. One of them is called the maximum likelihood estimation. Yeah, can you please mute yourself? Anyone please mute yourself? Okay, so as I said, this one, every term of this posterior, this is a posterior, is given to us. And B of X is the evidence of the feature X, where X can be one dimension or multiple dimensions. And this is a constant. Why this is a constant? Because it is not related to any class. Well, there is no term here. There is no term here referred to omega I or omega J. It's just Bx, is that right? And we have dealt with this one last time. Today, we will be extending this not only with one feature, we will have multiple features. But before doing that, let me solve this last example about the single feature of BDT, Bayesian decision theory. So we have assume that we have two classes. One of them is omega-1, and the other one is omega-2. And we have a total number of people in those classes is 100. So 40 people are classified to be omega-1, and 60% are classified to be omega-2. And we know that from this kind of data set, we have 40 and 60, we can definitely calculate the prior. Is that right? We can calculate the prior. We will say, for example, with omega-1, we have 40 people. Then with omega-2, we have 60. This means B of omega-1 is the number of samples in class 1 divided by the total number of samples. 0.4. And then we have B omega-2, the prior of class 2 is 60 divided by 100, which is 0.6. We know that, is it right? And now if I ask you, based on those prior knowledge, based on those prior probabilities that you have, can you classify any new sample that you haven't seen before? What you will say? You will say, okay, B omega-2 class omega-2 is more likely to happen. You will say, okay, the new sample that, or the unseen example, will be classified as omega-2. And we have a problem with that. We explained that last time. He said we have kind of a fixed decision all the time. Either if you have one in omega-1 or in omega-2, it will always decide for omega-2. Then the error is becoming 0.4. Is that right? Which is 1 minus the accuracy. It's 0.6. So now with adding observation or a feature to those like samples, the new samples or the old samples, we have like a feature is called x equal 1 feet. A person has 1 feet. Okay. And x equal to 1 feet. So we have 20 of those 40 belong to class omega-1, and 20 of those and 10 of those with feature 1 is belong to omega-2. So we have 20 for omega-1 and 10 for omega-2. And we want to find what is the posterior probability when x equal to 1 given omega-1 or given omega-2. We want to see if there is a new person with this kind of 1 feet. We want to see, we'll go to omega-1 or omega-2. What do you think? I'm not going to solve it before I hear like your opinions. So you have prior probability 40 and 60%, and you have a features 20 and 10. What do you think about the decision? Just give me an estimate.
I think I would go towards omega-1 just because the likelihood of that feature appearing in omega-1 is greater. If you just look at like 20 is half of 40 and 10 is 1/6 of 60. So then that feature is more likely in omega-1 than omega-2.
Yeah, that would be correct. Yes. So if we don't want actually it's good actually to answer like by unmuting yourself. But if everyone is unmuting at the same time and we have around 90 students or more, then we'll have a problem with that. Maybe it's the better way is to just write it in a chat. But thank you so much. This is a very good answer about what is the estimation of classifying this new sample, unseen sample with feature x equal to 1 feet. So we have B1 and B omega-1, B omega-2. Then we need to find what is the probability, the x equal to 1 given omega-1. This is kind of the likelihood of x equal to 1 given omega-1. So it's clear from that one, is that right? It's like 20 divided by 40. Again, as I explained last time, this is a conditional probability. We don't want to divide by the total number of samples. We divide only by the total number of samples in omega-1. That's a condition. It's actually 20 divided by 40. It's 0.5. Then we have the other one, x equal 1, condition omega-2. The likelihood for being in omega-2, it's called like 10 divided by 60, which is 0.6, which is 1/6, or 0.17. So now we have all of those. So what do you think about bx equal to 1? the evidence of a feature is equal to 1, you can actually like have it from here, which is 20 plus 10 divided by 100. It's 30 divided by 100. Okay, it's 0.3, thank you. So there is a question here. Why do we write x equal to 1? So x is a feature. X is a new observation or a new like information about what is the height of the person. It gives us more information. If we have a height of persons is 10 in that class, 20 in that class, it gives us more information about the samples itself. It will help like optimizing our classifiers. Is it a different feature, different number? Yes, this is like a feature. X is a feature, but x equal to 1 is a number. Maybe x equal to 2 is the same feature, but a different instance. You can think about B of x omega 1 as a normal distribution like this, and this is x. So we have here x equal to 1. We are talking about this point. Probably someone will say, if x is equal to 2, maybe I will get it here. And we want to see the density of this feature belong to x omega 1 or omega 2. Yes. Imagine, assuming we didn't have, no, for this kind of like BDT, we need to have most of the information. But if you don't have, then we will be estimating them. Anyhow, for Bx equal to 1, we will not need it because it's related. It's not actually, it's regardless of omega 1 or omega 2. Okay, there are many questions here. Is by increasing the likelihood and decreasing the prior and vice, should we get closer posterior for both of them? Yes, that's true. So because the posterior is relying on two things. If you go back, the posterior is relying on this term and this term. It's kind of balance between them, is that right? If one is increasing other than that one, then we might be biased on the posterior of omega I or omega J. It's actually kind of a balance between two components that will determine what should be the posterior. So now Bx equal to 1 is 30 divided by 100, which is 0.3. Is that right? Also, we can calculate this one from a different way. X equal to 1 and omega 1 plus probability of x equal to 1 and omega 2. This is joint probability, and we explained this one last time. And then if you did this one, if you calculate it as a conditional times probability of B1, a conditional times probability of 2 or B2 or omega 2, you will get 0.3. But for the time that we just calculated as this one. So now let's do the Pias rule. So we have B omega 1, x equal to 1. This is the posterior. And we have everything is given to us, is that right? 20 divided by 40, the likelihood, times the prior divided by 0.3. If you calculate this one, you will get 2 divided by 3. So this is the posterior. When we say x equal to 1 is x equal to 1 belongs to omega 1, or the sample, the people, the person of height 1 feet belongs to omega 1. Let's see if we have B of omega 2 where x equal to 1. So if we did those all numbers that we have, it's 10 divided, you might check those numbers, 60 divided by 100, prior divided by 0.3. Again, see, this one and this one are same. That's the reason why I'm saying in most of the cases, all the cases, you don't need to calculate Bx. For example, in the midterm or the final, if there is a question like this, you don't have to go with this Bx. You just ignore it. But we calculate here for convenient, and we calculate because the total probability of posterior omega 1 and the posterior omega 2 has to be 1. Without this B of x, if you didn't include it, the summation is not equal to 1, just for convenience. Okay, if you did this one, we will have it as 1 over 3. So now the decision rule is saying that omega 1 x equal to 1 is greater than B omega 2 x equal to 1. This is 2 divided by 3. This is divided by 3. then we will have omega 1. Same as to the answer that how did you cancel if they are two different equations? They are actually two different equations, but we are actually dividing by the same constant. Is that right? Dividing by the same constant. I am not canceling them. I am not canceling them because they are in two different equations. I'm saying that the influence of this bx on bw1 x equal to 1 is actually same as the influence of 0.3 on omega 2 x equal to 1. So if this one is 3 divided by 0.3, this one is 4 divided by 0.3. This one and this one can be cancelled. They have the same division. Okay, thank you. Okay, yeah. Okay, so this is actually what we did, and this is the last example about BDT with one feature. Okay, today the most important thing is we can extend this to multiple features. But before doing that, last time we actually found there is like two different ways to do classification with this BDT. One of them is saying that you will calculate it as this, same as what we did in the example. Then you decide omega 1. Or you will calculate it as this one without the denominator, b of x, we ignore it. Then you will say it's omega 1. However, we might have a problem with this because we don't want to keep just like calculating or computing b. What we need to do is we need to transfer this into function. And that function is called g1 of x, which is a discriminant function. It's a function that will differentiate between class 1 and class 2. So we have this one, we represent it as, if we take the natural log of this and this, we will have it here. And I explained last time, why did we have natural log? If anyone knows the answer, just let me know. Why do we have a natural log? There are many reasons for that. It's monotonically increasing. It's cancel the exponential. This is a very good point, actually. It simplifies the math. Because when we deal with normal distribution, either univariate or multivariate, we will have a lot of exponentials. And to cancel those exponential, we can deal with natural log, which is monotone increasing. Our exponentials, okay, that's a good one. Turns multiplication. Yes, that's also another way of understanding the natural log. It turns multiplication and divisions into subtraction and addition. Is that right? We will talk about this one when we have like a multivariate. So if we deal with this one, log of bx omega 2 plus ln omega or log omega 2, and then we will have this one as a discriminant function. We will call this one as a log likelihood. So now your posterior or your discriminant function is actually related to how much is the likelihood and what is the higher probability of class 1 and class 2. Two things to deal with. So now the classifier can be summarized as this one is greater, or this one is greater, omega 1 and omega 2. If you want to choose to go with another way of expressing this, you can define one discriminant function, which is g1x minus g2x, and then you will not compare either greater or less. Is that right? You will compare the sign. If the sign is positive or if the sign is negative, and you will have omega 1 and omega 2. I think this is clear. I'm just summarizing what I have done last week. So now, to find the decision boundary, so now assume that I give you a point, you classify this point based on the posterior. Now I ask you, what is the decision boundary? And we know that the decision boundary is the critical boundary that differentiate between class 1 and class 2. Is that right? If any sample is located on the decision boundary, then we will not be able to classify. We want to define what is decision boundary. One of the definition is this: if both of them are equal, add the feature x. Okay, we will answer those questions later on. So we need to define the decision boundary if they are equal. And we actually dealt with last time with two examples. We say we have a normal distribution, one feature, it's x. Here is one feature, x. And we have the same variance. This is the mean of 0. This is the mean of mu1, which is a scalar. There is no vectors here. It's all one dimension. And we plot those two actually normal distribution. The intersection between those two normal distribution, because it's one dimension, we have only one point. And this is the point where g1 of x equal to g2 of x. This point is only for the likelihood. Is only for the likelihood by ignoring the prior. We assume that the prior are equal. Is that right? And we will see when the prior are not equal. So here is the point. We call it x star. If the likelihood that you calculated is actually in this region, you will say it's omega 2. If it is in this region, you will say it's omega 1. And that's the reason why I say region 1 for class 1, region 2 for omega 2. And this is the boundary. Makes sense? Again, since both of them are identical with the same variance, there is no intersection except x star. This is one thing. So now, what do you think if we have the prior? If we have, this is the case where b omega 1 is equal b omega 2. So what do you think about if b omega 1 is not equal to b omega 2? Will we still have that point halfway between mu1 and mu2, or it will be shifted right and left? Shifted, but where? If b omega 1 is greater than b omega 2, where we will shift this point, critical point x star, the boundary? We'll be shifting it to the right or to the left. This is actually toward omega 1. Think about it. If then shift right. Yes, exactly. So if b omega 1 is greater than b omega 2, then we will have shift to the right. Why is that? Because when the prior probability of omega 1 is bigger, we give more chance, more space for that class to take a region off. Then we will actually shift it to this way. Don't worry about this one. We will have a lot of examples about this when we consider like different. It will be shifted like this one. B omega 1 is greater than b omega 2. We will shift x star from the middle, the halfway, all the way to omega 2. Means we are actually tightening omega 2 because it has less prior, small prior. Makes sense. Okay. Okay, this one. So now assume that we have two different normal distribution, two different means, two different variances with one dimension, x. Is that right? We solved one of the examples last time where we have this situation. So we know that the mean will determine the center of the normal distribution. The variance will actually spread it out or make it tight. Is that right? So if the variance of this one is greater than the variance of that one, this is 2, this is 1, square, we might have something like this. Since this one is tightening, it goes to 0 slowly. This one goes to 0 quickly. We might have a point here. Is that right? And we have a point here. Therefore, we will not have only one region, like R1 all the way and R2 all the other way, two sides. Or you can actually thinking about a surface, you actually divide it into two subsurfaces, positive side and negative side. Here, we will have this one is R2 because the yellow curve is still bigger than the green one. That's R2. And we have here is R1, and that one is R2 too. So you have two multiple regions connected to each other. That's not easy to deal with. That's when we have the variance is different. I hope this is clear. It's all a revision of my last lecture, and it takes almost like 30 minutes. Okay, so let's move forward with today's lecture. So today we'll talk about, we will extend BDT to multiple features. We'll talk about multiple features. All the time that we had before is X is one feature. Now we have X as a vector. So let's say we have X is equal X1, X2 is column vector, XD, where D is the number of features. Is the number of features. So you can think about it as the nose, the ears, the color, the size, whatever, the lightness. There are many features that we can get from the dog and cat. Is that right? So now, when we have one feature that I explained before, we call it univariate. And we have only two parameters, the mean and the variance. and it's represented by n normal, mu, and sigma square, where the BDF, later on we'll be calling it as the likelihood 1 over 2 by sigma exponential x minus this is an easy one that we have deal a lot with this one. It has two things, the mean and the variance, or the standard deviation without square. Is that right? So now it's kind of a relation between what is the location, the position of a future x from the mean. Well, if the position of the x is far away from the mean, it will be classified for the another cluster, for the another class. Is that right? If it is close, the minimum distance between them is close to omega 1, they will say, okay, it's omega 1. Think about it like this way. This is class, this is the mean, and I have a point here. Is that right? And we have another class, which is here. This is mu2, mu1, and this is x1. What actually is doing most of the time, either now or next time, is we just care about the distance between the position of this sample, either in one dimension or multiple dimension, and see how far is that from the center. Well, if it is close to the center, means it actually follows the same behavior of the data set of class 1. If it is far, then it has different features than belong to omega 2. This is the whole story of normal distribution. That's why we care about this one. This term is not important because it's a constant. This one, usually we cancel it, but we do care about this. X minus mu square. Okay, guys, I'm trying to go slowly, but there are a lot of stuff. So now we have multivariate. For multivariate with normal distribution, we have n, which is mu, and covariance. So now we don't have a variance. We do have a covariance because we have multiple dimension, multiple features, and we want to study the behavior of feature 1 and feature 2, feature 1 and 3, feature 1 and 4, so to see how they can tell us about each one. Is that right? And we will study different cases of those multivariate. So now this one is a vector. This one is a matrix, and I will explain each one alone. So now the probability of x, this is a vector x, multi-dimension, x1 to xd, is 1 over 2 by d divided by 2, number of features divided by determinant, half, then exponential. Again, we have exponential because it's normal, and that's the reason why we are doing natural log. We want to cancel it. We will explain this one. So we have minus 1 of 2 x minus mu transpose x minus mu. D is the rank of x because features are different. Is that right? Okay, so now instead of having only the distance square x minus mu, now we have a very big thing. Is that right? We have a very, very big thing. It's kind of Euclidean distance, different distances. There are a lot of different distances that not Euclidean distance, but we will go one by one. So now don't worry about this. This is the determinant of the covariance matrix, which is d times d. We will explain. And this is also a constant, and that's what we care about. How far x from mu times the behavior of those things, of the features together. This is kind of a behavior of the covariance matrix. So now what terms do we have here? We have x, it's the vector, column vector of the features. We have mu. Mu is also a vector because we have like dimensions. So mu is the expectation of x, which is mu of x1, feature 1, feature 2, feature d. Is that right? So if you think about it, two samples, x1, x2. This is feature 1, feature 2. Now you have thousands of samples. What is the mean? Is the addition of this feature. So each mean will have the addition of all the features divided by the number of samples. That's actually what they mean. We will have an example about this. So now we will represent it as a column vector, d1, d2, omega, or mu d. Is that right? This is d times 1. And you need to be very careful with the dimension when we have kind of multiple dimensions. And sigma is the matrix is in R d times d, in the dimension of d times d, size with ij element. This is the covariance metric that we explained in the second lecture. So it has kind of this dimension, d times d, where this one is the covariance interaction between the feature and itself, 1, 1. Feature 1 and itself. Now we want to see the correlation between the feature 1 and 2. This is called sigma 1, 2, and so on up to sigma d, 1d. Similarly, all the metrics between the correlation between all those covariance metrics, and it's represented by the expectation. Okay, we know that if we have a covariance of the same feature, we will get a variance. This is actually a very simple linear algebra identity. So we have sigma 1 squared, sigma 2 squared, sigma d squared. This is called the diagonal elements that we will be dealing it in case 1, where we have all of the variances are same. Okay, so now if you have for n samples, you will divide by n, where xi of k, the first sample of feature I. This is the mean of feature I. This is the first sample of feature j and the mean of feature j. Okay, this is for n samples, and this is for 2 samples. Let's take this example that we had before, but I want to do it again. That's because you will need to do it in the exam. You will need to find the mean, the variance, and covariance. Without those parameters, you cannot actually find the posteriors or the discriminant functions. Those are the parameters that we usually estimating them using machine learning, but so far we haven't dealt with that. We just calculating them using math. So we have 4 samples, and you can see how many features do we have from those 4 samples, S1 to S4. How many features do we have? Exactly, we have 2 features. Is 1 for the nose size, for example, 6 is for the ear size. Is that right? This is just an imagination. So we have mu is equal mu1 for the first feature, mu2 for the second feature. This is mu is a vector. Sometimes I write it as a vector like this. Sometimes they write it like subscript down. But in the exam, it will be things will be clarified. This will be bold, small letter. If it is a matrix, bold, capital letters, and so on. So now mu1 is equal 1/4. Okay, someone has already did that. How do we know there are 2 features? We know there are 2 features because it has 2 dimensions. So 1, 1, 6, it's actually belong to x1, x2. 2 features. Think about it as 2 dimensions. x1, x2, and this is the point x1 and x2. 2 dimensions, 2 features. Is it right? Then if we have 3 features, or 1, 6, and 8, then we will have 3 features, 3 dimensions. I hope this is clear. So if you add all of those, 1 plus 2 plus 3 plus 4, this will give us, I think, 2.5. And that will be 4. I will not calculate it. It will be 4. So now, with those things, we need to calculate the omega 1 is omega 1 square. I think it's 1.25. And then omega 2 is equal 1 divided by 4 summation x2k, this is over k, minus mu2 square. This is 2.5. This is just the variance between the 2 features, same, because it's for 2, feature 2 and feature 2. It's the variance. So now we have, how is mu2 is equal to 4? Let me calculate it again. Is 1/4, 6 plus 5 plus 2 plus 3. Okay, I think you got it. Okay, so now we have the covariance is sigma 1, 2 is same as sigma 2, 1. And this is one of the main features. Then this is one of the main identities of covariance matrix. It's symmetric, is that right? It's actually same around the diagonal. So we will say here is 1/4 summation k equal to 1 to number of samples for x1k minus mu1 x2k, the second feature, You will do the same for all of them. You will get this one is minus 1.5. And now the summation, the covariance matrix is going to be sigma 1, 1, sigma 2, 2, sigma 1, 2, sigma 2, 1. 1.25, 25, minus 1.5, minus 1.5. Remember, those are equal. In every case of the covariances, those are equal because the interaction of x1 and x2 is same as the interaction of x2 and x1, similarity. Okay, what is the second parameter? Now, when we go back to our main question, we talk about this one. It's only this one, the covariance matrix. Is that right? What other parameters do we have? The inverse. We know that the inverse of a matrix has the same dimension. So we have here 2 times 2, the inverse is just what? 2 times 2. And you need to know how to calculate the inverse of a matrix, 2 times 2 or 3 times 3. 3 times 3 is very rare to give you in the exam, but 2 times 2 is very possible. And then this is a scalar, pi over 2 to the square of d. This is transpose, like you switching between rows and columns. This determinant is a scalar. And we have this one is called the Mahanovich distance or square Mahanovich distance. It's kind of same as the Euclidean distance, but it has a multiplication of sigma square, sigma inverse. So now going back to the multivariate equation, I'm asking, what do you think about this term? Is this term a vector, a matrix, or a scalar? This term, what do you think? Scalar? Okay. Let's see. Is that right? Let me see. Let me make it small. There are many, many answers here. Scalar, scalar. Exactly. That's actually the point. We want to see what is the probability density function of a feature V in that plot of a normal distribution. It has to be point. Is it right? This is a constant. We don't care. This is just a scaling. And that one is a feature. So what do we have here? We have 1 times d. I think someone has actually wrote it. 1 times d. Dimension of this one is 1 times d. This is d times d, this one, and this is d times 1. So when you do the calculation, those will be canceled, and the results will be canceled. So you will have 1 times 1. So it's scalar. Is that right? So you will be actually saying that it's a vector, row vector, a matrix square, then you will have column vector. This is how it is. 1 times d, d times d, d times 1. The result will be scalar, which makes sense actually. It makes sense because we don't want to have a matrix or a vector. We want to have a point that will give us how much likelihood of those features belong to omega 1 or omega 2. If it is greater than, and then we'll have, based on those, so mu will determine, we want to mute. Okay, let's go back to this one. So now we have mu and we have sigma. Mu actually will determine the center of the class. And sigma, what do you think about sigma? Will determine what? Will determine the shape of the class. You might have something like this. Those are samples around. This is center mu1. This will be determined by sigma. You might have a different one, it's circle or eclipse, whatever, bigger or smaller. Those are points around my class with same behavior of features. This is mu2, and this is sigma 2. This is sigma 1. So we have two parameters, same as what we have for the univariate. We have mean and variance. Here we have the mean, which is the center, and the covariance, the correlation between those features. Okay, we will have 5 more minutes and then we'll stop for 10 minutes. So the covariance, multiple classes may have different distributions within the feature space. So assume that we have an example, 2-dimension. This is x1, this is x2. You might have something like this. You might have something like this. You might have something like this. Yeah, this one, yeah, that's a good question about the notation, but we will actually differentiate it. So this one is a summation. This one is like this sharp is a sigma, but in the exam, it will be differentiated. Here, this is like sigma, this is a summation. Usually when we write summation, actually this is also another difference. When we write summation, we have to write k, summation over k equal to 1, 2, 3, 4. But when we have sigma, it's like without anything. It's I, which is for class I or class J. So this is omega 1, omega 2, omega 3. This is mu 1, mu 2, mu 3. And then we will have sigma 1, sigma 2, sigma 3. Is that right? So now this is like a small example about 2-dimension space. Each class has different or equal. We will study all those possible cases today. It might have same sigma, same mean, different sigmas, different mean, and whatever. If they have the same mean, that's a very big problem. Is that right? They will all overlap each other. But we will not have that case. So now the next step that we are going to do is we will be looking at how unseen sample with a feature x as a vector, multiple dimension, to be classified based on normal distribution. We will be model that normal distribution, and we want to see if there is any new sample we want to classify it, either for omega 1, omega 2, or omega j and I. I will leave this one for you. This is just like a hint how to calculate the inverse of a matrix, 2 times 2 and 3 times 3. But we'll be moving forward with this one. Okay, I will stop here. If you have any question, just let me know before we continue with this stuff of discriminant normal distribution. Yes, this is the start of the break. We will continue at 7-9. Okay, so we have a question here. The lab is due before our demo. So the lab report is due on February 6th, and that should be the end of next week. It's the Friday of next week. So yes, you will be able to do your demo, and then the next day that you will have on Friday, you will submit your report. We will have the formula sheet on the midterm and the final. Yes, I guess so. And you might be able also to bring your formula sheet one-sided. The only thing that you might be concerned is you need to review your linear algebra, or you need to write most of the formulas of linear algebra. Yeah, I will actually like announce about what type of formula sheet that I will, but it's one ledger size preferred, or one letter. I think I will check what size of the letter that I actually announced last year. But it should be enough. One-sided will be enough. It can be written by hand, or you can just write it on the iPad or tablet, whatever. That should be fine. Okay, let's continue this one. So now our main point that we are going to in is we want to classify new samples either to class 1 or class 2 based on normal distribution with multiple features. First of all, we said, why do we need log likelihood? Why do we need log, natural log? We said because. And then we have gi of x is given to be the natural log of the multivariate Gaussian distribution. Is that right? The whole thing plus the log of bi. This is the likelihood, which we actually model it as a normal distribution with multiple features, is this one. We know that when we have natural log, this is log, denominator, and the whole thing is numerator. Is that right? You can think about it as y divided by x squared, which is log y minus log x squared. Is that right? And this also can be written as minus 2 length or log x, because this exponent will be actually in front of the length. Is that right? That's a very simple thing from linear algebra. We will do the same for this. So now gi of x can be written where x is a vector. It's minus d divided by 2 log 2 pi minus half log the determinant. Then we have minus 1 over 2. The log will be cancelled with the exponential. We will have only those long term. Minus half x minus mu I inverse x minus mu I, and this is transpose. It has to be transpose for the multiplication, otherwise it won't give us scalar, it will not work. And plus the log of the prior. So now we do have those terms. This is a constant that I will not care about. It's constant for every class. So we have a parameter here is sigma I, and we have also mu I. Those are the parameters that we will play with and we will try to find. But before that, we will have to consider 3 different cases. This is the first one where we have features are independent. They don't rely on each other and they have the same variance. So we will say then our covariance matrix, it's sigma square I. It's identical. So it should be something like this. Sigma square 1 all the way sigma square d, and I will explain this. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. It's only diagonal, and all of the covariances are not correlated. That's what I mean by independent. sigma ij is equal to 0, sigma ji is also equal to 0. We will explain that. Can anyone give me some examples about those independent features? Independent features mean that knowing about one features will not help you knowing about the other one. Will say nothing about the other one. Is that right? That's how we say about independent. Okay. Coin toss and dice roll. Yes, this is one example. Okay, knowing the temperature and passing the exam. Is there any relation between that? Probably if you are in a good mood, probably you will have a good midterm or final. Eye color and nationality. Yes, that's another example. They are not independent. Knowing that one feature will not help me to know the other feature. Those are independent. This is the first case, and it is very important. It's the ideal case, but it's very important for analysis and also for questions. The second case, where the covariance same for all classes, which is sigma I, let me write it here, sigma I is equal to sigma j is equal to sigma. It's one common sigma for all the classes. But the variance is different. The variance is different. Is that right? The variance of the features are different. Okay, we'll go one by one. The third one, this is 2, 3, which is arbitrary. So means that each class has its own sigma. Sigma I, sigma j, they are not correlated, they are not dependent to each other. That's the most difficult case. The case 1, when we have sigma square I, this is called uncorrelated. Uncorrelated means there is no covariance behavior between the features. And you can prove it like this way. So you have the covariance ij between I and j, random variable I and random variable j. It's written as this, which is the expectation, xi minus mu I, xj minus mu j. If you expand this and take the expectation, so you have xi, xj multiplication, and you have another multiplication, this is multiplication, and other multiplication, you will get this. If you do all those things, you will show that this sigma ij is equal to sigma ji is equal to 0. Means they are uncorrelated, independent, okay? And sigma I is the expectation, which is given to be sigma square. So now you will have the covariance matrices to be sigma square, sigma square, sigma square. Diagonal have the same. All of the features have the same variance, and they are not correlated. They are not independent. 0, 0, 0, 0. I hope this is clear. This is how we write it as sigma square I, where I is the identity matrix. I is the identity matrix. It's going to be 1, all the way 1, 0, 0, 0. This is called identity matrix. It has only ones or on the diagonal. This is one case. Is that right? So now, if I have this one, this matrix, which is D times D, I'm still D times D, where D will be denoted either here on the exam for the number of features, C will be denoted for the number of classes. Those are two differences. So what is the determinant of sigma I? Anyone can help. The determinant of sigma I. This is the most easier mu of them all. Okay. Multiplication. That's true. Yeah, so it's the multiplication of all of them. Why it's 0? When we have something like that, something like this, the determinant is just the multiplication of the diagonal elements, which is sigma square. All of them is D. It's sigma 2D. This is the determinant. Is that right? You can think about 2 like 2 times 2. Sigma square, 0 and 0. The determinant is just the multiplication because the other ones are zeros. Okay, how about the inverse? You need another one to help me with the inverse. I'm waiting. I will let you know. I will let you figure it out. So the inverse is 1 over sigma square. It's one dimensionless. Inverse the diagonal. Yeah, which was like this, inverse the diagonal. But let us write it like this way. It's the more convenient way. Is that right? It's actually easy to find the inverse of this one. Why? Because the inverse, it's 1 over the determinant. Then you will have to do is the cofactors. The cofactors of this one is this diagonal with one dimension less. Is that right? So you will have sigma 2d divided by minus 1 divided by sigma 2d. Those will be cancelled, and we will have only sigma square. Is that right? This is actually how you calculate it. You go one by one, but you don't need to do that. For identity matrix, it's just 1 over sigma square of one of the elements, time the identity. Okay, so now let's move forward. Let me see if there are questions. And I is the diagonal. I is the identity matrix. I is the identity matrix. It has a diagonal of 1s. All of the other elements are 0. Okay, so now do you only consider? No, we consider all the cofactors, but it's just for short of time. Sorry, I didn't get that part. So here, for example, here, when you have the covariance or the inverse, how do we calculate the inverse? The inverse is calculated by 1 over the determinant of all the cofactors, C11, C21, Cn1. Is it right? When you take these cofactors, you skip this and you skip this, and you multiply those things, the determinant. And you will do the same for all of them. You will get it like 1 over sigma square I. I think those who didn't understand this, please review your linear algebra. So now we have this one. Gi of x is equal minus d divided by 2 log 2 by minus 1 log sigma 2d. Is that right? That's the inverse. And we have minus 1 over 2 sigma square x minus mu I transpose x minus mu I plus the log of BWI. What I did, I just replaced this one, the determinant, with sigma square 2d, which is here. And I just replace this one also in the denominator, which is 1 over 2 sigma, like sigma square. It's from here. I want to go back to this. I replace this one, 1 over sigma square identity matrix. Identity is gone. We don't care about it. And we replace that one. So here is what we have. So what do you think about this? This term. This is constant. Let me cancel them out. This is a constant. This is constant. And we care about this and this. Why those are constant? Because they're actually repeated for this gi of x and gg of x. Same. If you add plus 1 and if you add plus 1 to all of the terms, we will not have any problem with that. Yes, we will have to do that in bx. Add minus, we don't need to add minus len bx because I said at the beginning, bx is just the evidence, it is the factor that are common for gix and ggx, but you can actually add it. You can actually add it, which could be like minus b of x. But this one, x, is not related to which cluster, either I or j. We cancel them. Thus, we cancel them at the very beginning. Okay, sounds good. I think it's clear now. So what do you think about this? X minus mu I transpose x minus mu I. We have covered this one in the first and second lecture. What do you think about this? This is actually the Euclidean square. Is that right? Plus log BWI. And we have 1 minus 2 sigma square. This is GI of X. So what I did, I cancel this, and I write this one, X transpose times X is the squared Euclidean distance, which is here. Is that right? Okay, so now the conclusion of this one, GI of X is 1 minus 2 sigma square plus log BWI. This is my classifier. For the first case, what does it tell? What does it tell? It tells out that the actually classifier for the first case, when we have independent features, we just really care about the position of the sample, how far it's from the mean, using the Euclidean distance, plus like a prior probability of BWI. So we will be caring about this term and this term. All other terms are gone. Is that right? So now if you have any question about this one, what you need to do is you calculate this log B omega I, and you calculate this one and calculate the Euclidean distance. Either this will be given, or you can calculate it from the data samples. This will be calculated from the data samples. What you need to do is you just find the Euclidean distance X minus mu I. So now, note, this is important. If B omega I is equal B omega J, then our classifier hello? Hello? Can you hear me? There is something. Okay, anyhow, we will have to continue with my device. Okay, we will not need the other device. So one of them is okay, it's coming back now. I don't know what happened. Okay, so now if we have equal probability, B omega I is equal B omega J, our classifiers will measure the Euclidean distance between the unseen sample X with all means of all classes. What do you think it will choose? It will select the minimum Euclidean distance, the maximum Euclidean distance, or what? It will select the minimum distance. This kind of classifier is called minimum distance classifier. Minimum distance classifier. It's a very simple one. It's very simple. Just you have unseen sample, you calculate the distance from this sample to each mean of the classes, and you classify. Is that right? Okay, this is if we have equal BWI is equal to BWJ, BWK, all of them are equal. Is that right? This is equivalent if you choose GI of X is equal to be the maximum. Is that right? Because -4 is actually greater than -5. This is equivalent if you say GI of X is greater than GJ of X. This means the distance to this is smaller than the distance to this because we have the minus. Okay, I hope this is clear about this. So now we do have this GI of X. when we do the classification using machine learning or any regression or classes, you calculate this, and you calculate the Gj of X, you calculate for K, different classes, and you choose which one is bigger. Or you say, I will choose only the distance, which one has a minimum distance to the center of my class. However, we also want to write it in a linear form. Do you think, can we write this case with the multivariate as a linear term? Can we write this one as a linear term? Yes or not? What do you think, guys? When we have a linear term, means it's a linear equation, slope times x plus b, the intercept. That's a linear. That's a very simple linear case. Is that right? However, when we do the multiplication here, think about this multiplication. Here is x, and there is x. When you multiply them, then you will have quadratic, x squared. When you have x, something in the middle, the other one is x. This is called quadratic. When you do the multiplication with the elements, you will get x squared. This is not linear anymore. Is that right? Let's see how this will work. Again, when we have something like this, we have a linear line, we have a plane or hyperplane. Those will be linears. But if it is quadratic, we might get something like this. The decision rule will be like this, or will be like this, or will be like this, whatever. We want to check if we can write that discriminant function of the first case when the features are independent as a linear or not. So what we do, this is our general form of a linear equation or a linear classifier. Is that right? This is like the bias. Let me write it here. And this is the weight. When we do the updating rule using machine learning and using gradient descent, we need to update this and this. What this weight will tell us, it will say how much a contribution of each feature to my classifier. Is that right? And you will be represented by, this is x1, x2, xd. Is that right? Those are units in your machine learning. Then you will have to multiply this one with omega 1, omega 2, omega 3. Those are the parameters that we tune. Is that right? We optimize to find how much a contribution of x1 to xd that will give us better optimization for my classifier. Then you will have a summation if it is linear, or you will have softmax, or you have different things if it is only one layer. But I don't want to jump to this because we will be talking about this one in details probably after the midterm. I'm just preparing you for the deep math so we can move forward with that kind of stuff. Okay, so we want to write this one as gi of x is giving to be like this. The first thing that you might need to do is you expand. X minus mu I, it's written as x minus mu I, the previous formula that we had, x minus mu I. When you multiply, this is x transpose x, x transpose x. So when we have something like this, just remind you, mu I of transpose, this is equal x transpose minus mu transpose. This is a linear algebra, is it right? When we have AB transpose, this is a different thing. It's it's B transpose, A transpose. We swap them, otherwise the multiplication will not work. Take two things in your mind, those two things. So now we have a multiplication, x transpose x, give us this term. This is the second term. This is the third term. That's the third term, the fourth term. Is it right? So now we expanded them. The main idea of expanding them, I want to see, do we have quadratic or linear? That's the main point. Okay. What do you think about this term and this term? X transpose mu I and mu I transpose X. Are those linear, scalar, vector, or matrix? Are they equal? Let me see if there is an answer for this. Okay, everyone said, a lot of answers said yes, they are same, they are same. Okay, they are same actually. Why? Because they do have the same dimension, but we swap. Is that right? This will be minus 2 mu I transpose X. They are the same scalars. The transpose of scalar is same as scalar. It doesn't make any difference. and we have this is constant, and we have this one, x transpose x. What do you think about this quadratic? Do we need to carry it in our derivations for the boundary, or we ignore it? Well, when I do gi of x, at the beginning, it's gi of x, but this one is x transpose x. This is independent for any class. That's the reason why we don't have quadratic for the first case. It's only linear. This one independent. This one independent, and that's the reason why we will be cancelled here, and we will have only this term. Is that right? Now, if you multiply it by 1 minus 1 divided by 2 square, sigma square, it's coming from here after we just do this multiplication. We will have 3 different terms. This is a constant at the end of the day. And we have this one is a term of x. This is a constant. The term of the x will be represented by omega. It's the parameter of omega. This will be represented by the bias. And we are done with the derivation. So what we will be considering, we'll be considering this one. That will be cancelled. 2 minus will be cancelled. We will have 1 over sigma square times mu it. 1 over sigma square times mu I transpose. Then we'll have transpose in the linear equation. It's here. The second term, we will have minus 1 divided by 2 sigma square, multiply this, which is here, plus the natural log, ln b omega I. And that will be called the bias. So now we could able to write the gi of x, the discriminant function, as a linear where it has a weight and it has a bias. This is the bias, this is the weight. Makes sense, guys? Let me see if you have any question about this. I can re-explain it again, but it's very straightforward. Go here. What we did, I expand this Euclidean distance as a multiplication. I found that it turns out those 2 parameters are scalars, and the transpose of scalars are scalar, same. And also it turns out this one is independent of any class. X transpose X is not related to the index I or index J. It's constant. They will actually appear in G of X and will be cancelled out when they make them equal. And we have only this one. This is related to X. I will represent this one as omega, my weight, and I will represent this one as my bias. And it has this very nice term. So now the linear, the boundary decision will be point if we have 1 dimension, as we explained last time. It will be a line if we have 2 dimensions. It will be hyperplane if we have 3 dimensions, and we will go over those in general. The second one, the second part of this case 1 is we want to find the decision boundary for case 1. In general, since we write it as a linear for omega 1, omega 2, we can just make them equal or difference and make it equal to 0. Either you choose with this one and choose this one. This is actually the way how do we calculate the decision boundary for any normal distribution or any different distribution. I make them equal for this one, which also equal for this one, and I collect all the possible terms. What I need to do, this term is of x. This term is of x. I will collect it. I did it here. Is that right? Then what I have, this one is a constant. This one is a constant, and we have plus ln or log b omega 1. This is plus. When you move it to the next term, it will be minus, and then I will have a division. It's here. Is that right? And that will be for bias. This will be for the omega, and we can explain it like this. And this is our decision boundary. What do we need to know about this decision boundary is 2 things. What is omega, the vector omega? What is the reference point? That's the only thing that we need to care about. You might be not interested in the derivation, take it for your reference, but you can follow it if you want to understand. But this is actually what we care about. This is the take home. We have omega t, which is the weight of our features, multiplied by a feature minus reference point. X0 is equal to 0. Well, you know that from linear algebra, the inner product, if the inner product of 2 vectors is equal to 0, means they are orthogonal. Is that right? That's the reason why we will say omega 2 and this term as is orthogonal to each other. So if we have A dot B is equal to 0, means A is orthogonal to B. That's the inner product. Keep this one in your mind. When we say inner product is equal to 0, means the angle between those two vectors is 90. That's orthogonal or perpendicular. So now we have this one where omega is the difference and x0 is a long term for the reference point. Let's see how can we plot this one. And we will take some cases. Okay, so now we want to find the boundary. G of I of x is equal Gj of x. And it's already written as x minus x0 is equal to 0. And we want to see how this is orthogonal or normal to each other. Assume that we have 2 dimensions. This is for case 1. I'm still in case 1, the very ideal case. So we have x1 and we have x2, okay? Assume that I have class. This is my class, mu1. This is another class, mu2. That's the mean of the second class. That's the mean of, this is omega 1, omega 2. So now we calculate that omega, the optimized omega that we are looking for when we do more lectures, is mu1 minus mu2. This is what we get from here. This one. That's nothing, is the only difference between mu1 and mu2. Is that right? I can represent it by a line connecting this one. This is my omega. So now, what do you think about the boundary? What do you think about the boundary? Where it will be the boundary? Do you think we will choose the boundary to be here? That's a very wrong answer, is that right? We will not choose it to be here. We will actually choose it to be ideally in the middle. We will try to choose it here. This is the boundary, we call it H. And this is normal, it's orthogonal. This is the reason why we are saying the boundary decision H, or the plane, or the hyperplane, which is a wall in 3 dimensions, it will be normal to the vector W. It has 90. So now, who will determine this position? Either in the middle, to the right omega 1, or to the right of omega 2, that will be determined by x0. So we have x0, and we have omega 2. Omega 2 will determine the difference between those 2 points. Omega x0 will actually determine the point either in the middle or not in the middle. Let's take special case, or case 1. If b omega 1 equal to b omega 2. Is that right? When we have this case and we have x0 is equal, let me write it from here. I don't memorize it. You don't have to memorize those long equations, but let me write it here. It's 1/2 mu1 plus mu2 minus sigma square, the Euclidean distance, log b omega 1, b omega 2, mu1 minus mu2. This is x0. I want to find what is the position of x0 if b omega 1 equal to b omega 2. What do you think, guys? When b omega 1 is equal to b omega 2, when the priors are equal, where did we have this? We have it last time, and also I review it in the beginning of this lecture. When they are equal, means this term is 0. This will be 0, because the natural log of the same number is what? It's 0, is it right? Then the whole term will actually cancel out. We will have to have x0 is 1/2 mu1 plus mu2. And this is nothing. This is the halfway between the class omega 2 and omega 1. This is the half, and this is x0. So now x0 is in the middle. If we have like equal probability of the priors. Is that right? This is one thing. So now, if they are not equal, if BW1 is not equal to BW2, then we will have a shift of that line, either towards omega-1 or towards omega-2. Let's see how this is actually related to what we have so far. I think you can see this one. Is it right? This is a normal distribution with actually two different means, but with the same variance. This is the point. This is the point, and I can plot this one. And here is my omega. The difference between the mean mu1 and mu2, and this is normal, which is my x naught. B omega-1 is equal to 0.5. B omega-2 is equal to 0.5, and this is only for one dimension. Is that right? You can look at this one. The likelihood is here, omega-1 is there, omega-2 is there, and we have this is a distribution. And now we can decide this is for omega-1, this is for omega-2, two different regions. Is that right? Things are clear because the priors are equal, and x naught is in the middle between them. Now think about higher dimension. When we have higher dimension and we have also linear discriminant function, then we still has a line. We still have a line. Is that right? This is 2 dimension, and we have a line differentiating between R1 and R2. This is the distribution of class 1 in 2 dimension. This is the distribution of class 2 in the 2 dimension. And this is the center of the mean. If you reflect it from the top, you will see here is the center of the mean for omega-1, center of the mean of omega-2, and there is like a line between them because those are linear. And it's actually coming from the fact that the one that we did is linear. This is linear. And also, this one is linear. This is the reason why we are having line. Let's see if we have higher dimension. When we have higher dimension, instead of having a point as this one, point here, or line in 2 dimension, we will have in 3 dimensions, we will have a wall or a surface. We call it surface. Is that right? It's like a wall separating this of 3 dimension of normal distribution in 3 dimension and separating this one. Again, this kind of a linear actually, like it's a plane. You can see it's a plane, and it's kind of a linear between omega-1 and omega-2, but that's actually equal if we have equal probability. It's in the middle. That's because the point x0 actually in the middle between all of them. But now with x0 is not like 1 point, which is 1. It might be 1, 2, 3 dimensions. I hope this is clear. This is just how to visualize the case 1 when we have independent features and we have 3 different cases for 1 dimension, 2 dimension, and 3 dimension. This is 3 dimension. Okay. So now let's see the impact of the prior. Now, if B omega-1 is not equal to B omega-2, if B omega-1 is greater than B omega-2, then the decision boundary moves away from omega-1. It makes space for omega-1 to decide more than omega-2 because of the likelihood. Is that right? It's more likely for omega-1 than omega-2. It will be closer to mu2. And the same thing is happening here. If B omega-2 is greater than B omega-1, then the decision boundary will move the way around from omega-2 closer to mu1. Let's take the examples here. I think I will enlarge so you can see. Now, instead of having B omega-1 is 0.5 and B omega-2 is 0.5, they increase this one into 0.7. Then the decision boundary, instead of being here at the beginning when they are equal, we push it a little bit away from omega-1. It gives a lot of space for omega-1 to decide. So most probably, most of the features that you might get will belong to omega-1. And the remaining is omega-2. So now if we increase the probability, higher probability, a little bit more and make it 0.9, then we are actually pushing this x0 from the middle all the way towards omega-2. making space for omega 1. This is for all omega 1, which is not good actually. Because if there is any future is becoming here, we will have a future for omega 1 and we have another value for omega 2. Probably we will be misclassified. Is that right? So we need to be careful with selecting our priors and also defining those equal probability and the likelihood. Similarly here, we have for 2 dimension, this is the point. Instead of it was like here, we push it a little bit, make it this small. And the same thing is here. See, this is only the region of omega 2. It becomes very, very small. And the whole region is become for omega 1, which is 0.99. Okay, so the take home for case 1 is very simple to analyze. It's easy to plot with 2 dimensions. And also it's nice shape. You can see most of the shapes, those are same. They are same. Why they are same? Because of our definition at the beginning, when we say is sigma square I. They have the same variance. So the tightness or the wider of those normal distributions are same. This is one thing. Okay, so what do you think about the impact of increasing or decreasing sigma square? What do you think? The variance. What will happen if we have small variance or big variance? So if we have small variance, that will actually play a role in x0. Let's go to x0. If this is very small, it makes this one is negligible. Is that right? It makes this one is negligible. They will intersect more. Okay. It will make this one negligible, and then we'll be coming back to the halfway point between mu1 and mu2. But if sigma 2 is big, then that will be a lot of difficulty. Is that right? They will have a lot of intersection. Let's see how this looks like. Impact of sigma square. Let's write it here. I have here 2 dimension, x1 and x2. We will have small sigma square. When we have small sigma square, do we have a bigger class or smaller class? What do you think? What should be the smaller? Is that right? Because we don't have spread out of the samples around the mean. They will be all dense around the mean. Then we will have tighter class. A lot of points here. If there are some samples, it might be here. Those are outliers. We ignore them. Is that right? And then we have another one. It's here. Is that right? Then we will say, this is our connection. This is our connection. And this is the difference, which is omega. And this is our hyperplane or plane. It's H, normal. So now, either we have like different priors or we don't have different priors. The value of sigma square will cancel that part of x omega. Then it will be in the middle. X of 0 will be like 1/2 mu1 plus mu2. So now let's check the other one when we have like larger sigma square. X1 and X2. Then when we have larger sigma square, larger variance, we might have a bigger class, and we have also bigger class. Then determining those like boundary will be difficult for us. It won't be in the middle. Why? Because the sigma square is bigger, and we will have to care about the prior probability. Then we might have this one, or we might have this one. Those are very critical because the points are distributed and they are mixing with class 1, and also they are mixing with the class 2. In these possible cases, then linear regression or linear discriminant function will not help. We will have to do some overshooting or some quadratic discriminant functions. Anyhow, this is for log sigma square. Okay, so let's move forward with an example. This is what you are looking for, guys. Is that right? A lot of you don't like a lot of theory, but we will have to mix with a few examples. Okay, so we have two different cases when we have equal prior, b omega I equal to b omega j, when we don't have equal. And we have also mu1 is given, mu2 is also given to us, and sigma is there. And this is definitely case one. Is that right? From here, it definitely case one. So it has independent zero covariance, sigma omega I and sigma ijji 0, and they have the same variance, 1, 1, or it can be 2, 2, that's fine, or 3, 3, but they should have the same variance. That's the reason why we call it independent and identical variance. Sorry. Let's keep this one. So the question said, find the decision boundary in both cases. What do you think about the decision boundary? We have two dimensions, x1 and x2. We need to write a linear equation of x2 in terms of x1 and find the line or the hyper between them. We will get like same decision boundary or different when we have two cases, equal priority, equal prior, and not equal prior priority. I will pause for a few seconds so you can reflect on this example, and then we will have to solve this. We will have different, yes, different decision boundary because of the prior. Prior will be shifting the decision boundary either to omega 1 or to omega 2. Okay, let's solve this example. First of all, we need to memorize that this is the general case of case 1 when we want to find the decision boundary. And this equation, from where it came from the fact that gi of x minus gj of x is equal to 0. All the derivations of this, from transforming it to ln natural log all the way, we get this one, where we have only two parameters now. We have the weight, which is mu1 minus mu2, the difference between the means of both classes, and we have x0 is the reference point. So the first part, when we have equal priority, first calculating omega. To find this decision boundary from here, we need to find omega and we need to find x0. We don't care about x. X is just like a random one, sample, x1, x2. This is what we need to find. When we have b omega 1 is equal to b omega 2, it's 0.5, calculating omega first is mu1 minus mu2. Don't go over this too much. 3, 1 minus 2 minus 2. Then we will have a vector of 3 minus 2 is 5. 1 minus 2 is 3. Okay, this is actually a very simple thing to calculate omega, which is the difference between them. So now we have a vector. The difference between omega, mu1 and mu2 is a vector that connecting mu1 and mu2. Calculating x0. We have x0 from here. It's half, the addition, the halfway. Those are equal, will be cancelled. The whole term will be cancelled. We will have only equal half mu1 plus mu2, which is half. Sorry. 3, 1 plus minus 2 minus 2. This is mu1, this is mu2, and this is summation. Makes sense? When you do the summation, you will get 3 plus minus 2 is 1 divided by half is half. And this is minus 0.5. That's actually what we got. It's easy to do. We calculate omega, the weighting vector, and we calculate the reference point. So now you will use those and plug them into omega t x minus x0. Make it equal to 0. That's the reason why we need to find the decision boundary. So omega 2 is 5, 3, but transpose, it becomes a row vector x1, x2, because we have two dimensions, two features, minus x0, 0.5 minus 0.5. This is equal to 0. When you do this multiplication, x1 minus 0.5, x2 plus 0.5, you multiply them, 5, x1 minus 0.5 plus 3, x2 plus 0.5. This is all equal to this is all equal to 0. If you do all this simple math between x and 1, x1 and x2, you will get x2 is equal 1 minus 5 x1. You do this one at home. I will actually post this one for you. This is our decision boundary. Is that right? So x2 is 1 minus 5 x1. For each x1, we might have x2. Okay, so the second one, we will continue the second part, not now, but we will have to take a break, 10 minutes. We will coming back at 8:88. I will be staying here. If you have any questions, just let me. Okay, so I have a question here. It says, I don't understand what the answer represents. The answer represents a line that actually making a boundary between omega 1 and omega 2. What you can think about this one as an equation. This is an equation, is that right? It has x2, which is y, x1 is x. Think about it like this. This is x1, this is x2, is that right? So now we need to plot this line. When x1 is 0, we have 1 over 3. When x1 is 0, we have this point, 1 over 3. This is what we call it the intercept. It's the intersection of y-axis or x2. Then you need to find different values of x1 that you will give us. You might have something like this. I don't know. You might get something like this or something like this. It depends on the slope. This is the slope. 5 divided by 3, x1 is the slope. Or you might get something like this. This is actually the best decision boundary between class 1 and class 2. That's what it represents. Make sense? This is what it represents. It is just a line because it's 2-dimension. If it is 3-dimension, we'll have plane. And this is class 1 and this is class 2. And here is the W, that difference between mu1 or mu2, mu1, and this has to be orthogonal. That's what it represents. So now, if you have any new sample, any new like unseen sample, if the sample is located here, then we cannot actually like classify because it's on the boundary, on the edge. It's not belong to omega 1, it's not belong to omega 2. But if it is on the positive side of the boundary, then we say it's omega 1. If the new sample that we are testing, it's actually on the negative side of the boundary, then we will say it's omega 2. This is what it explains by this equation. It's a very simple equation. It's a linear equation that will draw a line between the two features. I hope this clarifies the definition of x2 and x1. Okay, so for the formula sheet for the final and the midterm, most likely you will have a single-sided, one page, single-sided for the midterm, and I will also provide some formula sheets in the exam. The formula sheet that I will provide in the exam, it will be posted to you before the exam. So you want to see what is the difference that I didn't write, you can write it on your own. That's one thing. And it also the same for the final. But in the final, you might have two-sided. You can write on both sides. But I will making like a formal announcement about this, what type of aid sheet you will bring. And I will post my formula sheet for you at least 2-3 days before the exam. Okay, guys, let's continue with this. So now we calculated the decision boundary, which is a line, a linear line between x1 and x2 that will differentiate between class 1 and class 2. The second part of the problem is to find the decision boundary when we have different priors. So for different priors, I give like an arbitrary probability, 0.3 and 0.7. Since omega in both cases are same, which is omega mu1 minus mu2, we don't need to calculate it. It's already there. Where is it? It's here. mu1 minus mu2, which is 5 and 3. The only difference between the equal priority and unequal or the different one is x0. So x0 is now not in the middle between class 1 and class 2. And that's because we do have this term. This term is not vanished, is it right? So if you calculate this, so you will get this one as, I want to see my answers here. I don't want to calculate all of it again. So you will have to get point minus 0.8473. And this is as from before 5, 3. It's a vector. This is 1. I think this is 1 because it's 1 here. The variance is 1. Okay, can you see my screen? My screen is a little bit slow today, but anyhow. Okay, we can see it. And this one. Can anyone calculate what is the Euclidean distance? mu1 minus mu2. We have it here, 5 and 3, and I want to have the Euclidean distance. This is a very simple test for those who know linear algebra. Again, I'm saying mu1 minus mu2 is a vector, 5 and 3, and I want to calculate the Euclidean distance, the squared Euclidean distance. Okay. So it's simply just the square and addition, is it right? So we will have as, okay, so explain how you get the variance for the matrix. Okay, what is that matrix? Let me explain. I don't want to go all the way up. So we have this matrix, is covariance, is that right? It's 2 times 2. The first element is the covariance between a feature I and I, 1 and 1. We call it omega or sigma 1, 1. This is sigma 2, 2. This is 0, this is 0. This is where the features are independent. This sigma 1, 1, it turns out to be a variance, sigma square. And this is sigma square. In my matrix is 1, 1, 0, 0. That's the reason why I say it's 1. Make sense? Okay, so now I ask about finding the squared Euclidean distance of this denominator. We have it as 5 and 3. It is just 5 square plus 3 square. Is that right? Which is 34. Please review those things. I will write it here for your reference. We have the Euclidean distance. Is that right? Which norm 2 is the square root of x1 square plus x2 square for x vector. Now, if I use the Euclidean square, I will not have that square root, is that right? I will have x1 square plus x2 square. This is called the squared Euclidean distance. This is norm 2 and the square. So I just make it 5 square plus 3 square is 34. So when you do all those simple math, you will get this equation, and you will substitute x1 and x2, make it equal to 0. You will find a different decision boundary. And that different decision boundary, because we don't have an equal priors now. These are different now. Is that right? Instead of having a slope 1 over 3 now, sorry, instead of having an intercept 1 over 3 here, this is 1 over 3 is my intercept, the intersection of x2. Now I have it as 1.8 divided by 3. And we kind of have the same slope, but different orientation in terms of intercept. Because it's minus 5x, we do have minus 5x here. It's different orientation. So now you might think, why do we need this? The question is coming now. Check any point you might think in your mind and classify. And see what is your classification for part 1 and part 2. So let me write this question so you can do it at home. Check any point you might think of and classify. for part 1, for part 2. This will give you a hint how the prior will impact your classification. You might get this one, you might, I'm not sure. It depends on your sample. You might get omega 1 is here, omega 2 is there. You would choose this sample, please. X1 is 0.2, or X2 is 0.133. It's kind of, you have a vector of feature, 0.2 and 0.133. Check this point and see how it classifies. If you get a boundary or a decision is greater than 0, you will say it's omega 1. If you get it like less than 0, you will say it's omega 2. This is all about case 1. So we finish case 1 where the features are independent and the variants are identical. We actually find the linear discriminant function. We also derive the decision boundary from this linear property of case 1. So now let's move with case 2. We write gi of x again, the formula that we have before is equal minus d divided by 2 log of 2 pi minus half minus 1 over 2 x minus mu I transpose I inverse x minus mu I plus the log of b omega I. This is the one that we usually deal with because it comes from the posterior. We transfer it as a log and we write it as this one. If you want to write, you can also write log b of x, but we don't need to do that. So the second case where the covariance same for all classes, meaning that omega I is omega j is, or sigma I is equal to sigma j is equal to sigma. But they don't need to be necessarily have the same variance. An example of this, you might consider sigma for all classes is 1, 2, and then you will have here is 0 or whatever. It's maybe 1 and 3. This is one possible case. See, the variance now are not equal. This is one of the main differences between case 1 and case 2. And you will see that shape. The shape of the normal distribution for class 1 is different than the shape for class 2 because the variances are now different. Okay? This is one example of a sigma. Since sigma I is equal to sigma, then we have gi of x is equal. In general, this is a constant. We will not care. This one is what? What do you think about this? Will it be a constant or not? We want to see if you guys are following because I cannot see you. Sometimes I like to ask questions. So what do you think about this term? Will it be constant or not? It will be constant because with our assumption that covariance same for all matrix. Thank you. It's constant. Okay. Then we will have to have constant those two terms, this one and this one, minus 1 over 2 x minus mu I transpose inverse x minus mu I. This is the only term. In case 1, we do have the same thing, but that was, we call it Euclidean distance. We don't have this term. Now things are different. We have that term in the middle and we cannot get rid of it. Is it right? So we will have to deal with this. So this term usually we call this term x minus mu I transpose. Those who do research, maybe they know it. X minus mu I is called the Mahalanobis distance. Sometimes it's called the squared Mahalanobis distance. And the relation between this one and the Euclidean distance, if this one is identity matrix. So if Sigma I inverse is the identity matrix. It doesn't have any impact. Then we'll have transpose times the same thing. So the question is, how do we write this one as a linear form? And will we have a linear form or a quadratic form? Then we'll have X, because we'll have X transpose X. Same as what we did before. What we need to do, we start from here, plus the log BWI. You need just to multiply all of them together. X transpose sigma inverse X. It's this one. You do the same for all of them, and you will find out that this term is also independent. We are lucky with that. Is that right? Because now we are not dealing with a quadratic discriminant function. Linear is easy to do. It's just a line or a plane. But quadratic, it could be difficult. This one is independent of plus I or J. We will not care about this one. The second thing is that this term and this term are same. It's scalar with different things that we did before. The scale, transpose of scalar is scalar. So we will have only this one. This will be -2 sigma I. Sorry. Sigma I transpose inverse X. And we have this term as is, we have this term as is. So now when we do have this one, minus will be cancelled, 2 will be cancelled, we'll have only this term, and that term will go as is, and we will have log of BWI. The derivation, you can go over it. However, we want now to write it as a linear equation or a linear discriminant function. What we need to care about, what is the parameter in front of X? This is what we really care about. That's the weight. That will be the slope or the weight that we will be focusing on. This one should be a constant because it's not related to any X. This is constant, multiplication is scalar. This one is also a constant. This will be called as omega I0. This will be called as omega. And thus we came up with this linear equation. I hope this is clear. It's just like some steps that you need to follow when you derive this kind of things. So now when we have case 2, we find the decision boundary. I will not go over this proof, but I will ask graduate students to prove this. I said it's required for graduate students. You should focus with the same as we did before. G1 of X is equal G2 of X. We have here, you write this one as we did before, omega 1 transpose X plus omega 1 0 is equal omega 2 transpose X plus omega 2 0. You did all the derivations and you will arrive at this point. Similarly, here we have some of the observations that we need. The one thing that we need to clarify is the decision boundary needs not to be orthogonal in this case. Why is that? Because when we have the orthogonal things, omega transpose was mu1 minus mu2. It's the difference between the two means. Now, it's not mu1 minus mu2. We have to multiply it by sigma inverse. This sigma inverse will change the rotation of the difference between means 1 and mean 1 and mean 2. That's the reason why it's not orthogonal anymore. Again, I will repeat this one. For case 1, we have omega 2 is equal to mu1 minus mu2. It's just the difference between the 2 points, which is a vector. Here, we have the same difference, mu1 minus mu2, but it's multiplied by a matrix, which is the inverse. This matrix will actually change the rotation of this vector, and it will not be like boundary, normal on the decision boundary. It's not normal anymore. So this is the reason why we are saying here it's not normal. So for equal probability, BW1 is equal BW2, then we have X0 is equal 1 over 2, same as what we have before, because this term will be cancelled and we'll have only this one. So the reference point that is in the decision boundary will be the halfway between mean 1 and mean 2. Again, if the priors are not equal, then X0 will be shifted to the more likely mean. to the more likely mean. So some of the examples or figures that I would like to show is this. I will try to enlarge. Please analyze this figure in your mind and tell me what did you get. What is your observation for case 2 compared to case 1? Don't think about the impact of the priors. That one is 0.5, 0.5. The second figure, the right one is 0.91. That's okay. You're just shifting it. Think about the normal distribution, the shape of the normal distribution. Anyone has an answer for this? Red has more space. Can you just explain why is that? Why it has more space? The ability has larger area in case 2. Yes, that's one difference. The second one, because the boundary will be shifted. Yes. See, first of all, when we have equal priority, omega 2 equal 0.5, 0.5, or more likely, so shift to right. Yes, there are a lot of good answers here. First of all, think about the shape of the normal distribution for class 1 and class 2. Are they same? The shape. They are not same. They are not same because each one has a different variance. This is one of the most important things you need to think about. Again, let me write this one here. We said sigma is equal. It's equal for all classes, but you might have 2 here, you might have 1 here. The variance between the feature 2 and 2 is different than the variance between feature 1 and 1. That will create different distribution of the likelihood. That's the reason why you might have different shape, wider here and tighter here. That's because of the variance. Is that right? Even though the probability are equal, it's just to make sure the decision boundary is in the middle. It doesn't actually contribute or change how wider or tighter the distribution. This is one thing. The second thing is when we shift the x0 either to the right or to the left, then we will have wider for omega 2, tighter for omega 1. That's one thing. The third step, the third observation that you might get, the boundary is linear. This is one also important. See, when we have linear, when we have 2 dimension, it's a line. And also it is a line. Line is being shifted because of the priors. But most of the discriminant functions for case 1 and case 2 are linear. That's 2 things or 3 things that you need to care about. Okay, so let's move forward with case 3. Case 3 is the most difficult one. Will the boundary be rotated here? The boundary will not be rotated, but it will be shifted. We will have the third case where the boundary will be rotated. Yeah, we will have that case. But for case 1 and case 2, we will have a linear line or plane in 3 dimensions, for example, but it will be either in the middle, shifted to the right or to the left, but it will not be rotated. The only rotated is the difference between the means, mu1 and mu2, because of that sigma I inverse. Okay, so now let's go with case 3. We will not talk a lot about case 3 because it's not actually mandatory for this, but we will have to explain it and see how the shapes of case 3. Again, we go with the same fundamental of gi of x, which is this one. It's coming from the log likelihood or maximum likelihood. But now the differences is that each class will have its own sigma I. Class 1 will have sigma I, class J will have sigma J. They are different. And the only constant term is this. That's the only constant term. This one is different, this one is different, this one is different. There are a lot of differences in this case. So the posterior or the BDT decision will not rely only on the Euclidean distance or the other distance. It will rely on all of them. The log of sigma I determinant, it will rely only in the distance, it will rely only on the prior. So now if you expand this out, I actually wrote it here, it's all expanded, plus len bi. So now what do you think about this? What do you think about this gi of x? Can we write it as linear? or not? Think about it for a few seconds. Can we write it as a linear function or quadratic function or polynomial function? No. Why is that? Quadratic, yes. Okay, let's go term by term. We have this term, I don't care about it, quadratic, because we cannot cancel terms out. Okay, that's a good point. Thank you, guys. Let's go term by term. We have this one is a constant. This is not related to x, to my features. Is that right? I will have sigma I, take the determinant and make it there as a constant. The term that will actually determine if it is quadratic or linear is this. This is the one. Before, when we had case 1 and case 2, this multiplication was with sigma in case 2 and with variance in case 1. But now it's related to which class? I. So now we cannot ignore it. Then we will have quadratic x and x. You might have at some point is x squared. Is that right? That's quadratic. So when we have something like this, we need to collect terms. Is that right? This will be omega. We have also x will be another omega, and all the other things are, this one is the bias constant. So we have, it's not only something like this. When we have gi of x is equal omega I transpose x plus omega I 0. This is linear. We have this one and bias, but for quadratic and polynomial, extra terms will appear. Those extra terms will be related to x squared, x over 3, x over 4 when we have higher dimensions. But for this one, what we will get, you can get from this one is omega I as a matrix, this is a matrix, is equal -1 half sigma I inverse. It's coming from here. It's coming from here. This is the way that I will represent the quadratic. And then omega, the weight vector that we usually have for linear, it's going to be sigma I inverse of mu I. How did I get this one? It's from the x and the x. The term related to x, we'll call it omega. And the term related to this one is, I don't have this transpose. Thank you. Okay, so there are good students are following. We don't have that transpose. The transpose will be there in the equation itself. Okay, so we have omega and omega I. Then the remaining term that we might have is the bias. That's the thing that we usually do in machine learning, which can be a constant from the beginning, which is -1 log sigma I -1 over 2 mu I transpose this is I plus log dwi. Those are the terms, and we can write them as a quadratic form. This is a quadratic form. We have x squared, we have x, we have omega I 0, constant. If we have polynomial, we have x squared, we have x to the power 3, and then x, and then omega I 0. This is how the way that we'll deal. We will talk about polynomial and quadratic cases next time. Let's see how that will be different. So let me see, what did you get from this figure when we have case 3? I want to see your observation about those 4 different figures. Again, what you are looking here is the boundary linear or not linear? Is the shape of normal distribution same or not same? If they have the same kind, some of them maybe it's eclipse, some of them may be normal distribution as is, some of them is different. So what do you think, guys? I want to see your observation, and then we will have one example and we will conclude this lecture. Okay, let's go one by one. For this figure, what do you get? Rotating around the second one, exactly. That's because of the quadratic. Let's go one by one. So before, when we were doing case 1 and case 2, we had what? We had only one line because it's linear. Now we have actually two lines. Those two lines is a pair of hyperplane or a pair of lines. That's actually is the way that we can think about it in terms of quadratic. This is one thing. The second thing, it's this one is curved. It's not line anymore. Is that right? The third one, this one is x square. This follows the shape of x square. And here it could be like this. This is how actually we can see it. This is because of this term. The quadratic is actually rotate the decision boundary in terms of curveness. And here, this one, the whole thing is for the red, omega 1, for example. And the small one is a circle or eclipse for omega 2. And that's the center. This is the center. So now we do have different shapes for quadratic discriminant functions where we have. So how this can be related to what we will be doing in classification. One of the things that you might think of is this one. If I have linearly separable like x1 data set, x2, I have this one, this one, this one, this one, samples, and I have this one, this one, this one, this one, two samples. Definitely, those kind of data sets, you might have many classes. We can separate them by linear equation. It has an intercept, it has a slope. This one comes from case 1 and case 2. Is that right? It's easy it's easy to see this. We can see it from case 1 and case 2 because the discriminant function for case 1 is linear. The thing is the same thing for case 2. How about if we have this? I did a lot of, let's change this one. What do you think about this? We cannot make it linear. That's wrong. This is wrong, is it right? Some of them will be actually overlapping with the others. What we can do, we will have to shape it like this. This actually comes from case 3, where we do have quadratic. This is kind of quadratic. If you make it like this, it's like upward shape of x square, kind of. Or if you have polynomial, you can shape it like this. If you have some classes here. That's coming from high order of this term. This is the main reason, the main differences between case 1, case 2, and case 3. I hope this is clear now. So now let's take last example here. We do have two classes and two features. I have mu1 is 3, 1. Mu2 is coming from our data set. It's -2, -2. I have sigma 1, sigma 2 is equal, and we have 1, 0, 0, 2. Which case is this? Which case are we dealing with this in the example? Case 1, why? Case 2. Yeah, there are many answers. Case 1, case 2, sorry. Yes, why is that? Because for case 2, the sigma is same for all classes, class 1 and class 2, but different variances. Is that right? If I want to have it as class 1 or case 1, I will say sigma 1 equal to sigma, which is 1, 1, 0, 0. Both variances are same. Or I will say 2, 2, 0, 0. This and this have to be the same. Okay, this is for case 1. But for case 2, this one is different, this one is different. This is just an example. Sometimes we don't have to write this one as 0, 0, especially for case 2. This has to be values, not 0, 0. Means there is correlation between the features. But for easiness, just to make it easy for you guys, I put it as 0, 0. Okay, so what is the classification for X? The idea of calculating this, we will say, given a feature dimension X, which can be two features, compute g1 of x and g2 of x of case 2. Then you decide. Decide omega 1 if g1 of x greater than g2 of x. And decide omega 2 if g2 of x is greater than g1 of x. Okay, this is the main idea that we will be doing with. However, to find g1 of x and g2 of x, you don't have to memorize this in a linear form. It will be given to you. What you need to do is you need to calculate the parameters. You calculate the parameters, you plug into these equations and find g1 of x, find g2 of x. Okay, so what we need to do, first we need to calculate this, sigma inverse. We need also to calculate this one, this is given. We need to calculate omega I0. And then we'll be finding which one is bigger than the others. So sigma inverse is 1 over 2, the determinant. It's just 1 times 2. And then we swap them to find the cofactors. 1, 0, 0.5. Then omega 1 is just the multiplication. 1, 0, 0.5 that we just calculated now times 3, 1. So what do you think? We will get scalar, matrix, vector? You need to be careful with this. 2 times 2, and this is 2 times 1. This is same, we will get 2 times 1. The first row times the column, 1 times 3 is 3, and we have 0.5. This is the first thing that we calculate. So now omega 1 is given to us. I calculated. We need to find omega I0. Omega I0 is based on that equation. It's 1 over 2 mu1 transpose sigma inverse mu1 plus BW1. Are they equal? Yes. When they are equal, I will not care about this term. That will appear in the other g2 of x, and they will be cancelled out, or they will have the same contribution in both equations. This one is given. It's already here. We just need to multiply it by weight vector 3.5. I will explain why it's cancelled. This is omega 1, 0. So now you have omega 1 is here, equation number 1. I have this scalar, equation number 2, and I will put them in g1 of x. Put 1 and 2 in g1 of x. Therefore, g1 of x is equal omega 1, which is 3.5 transpose. We have x1, x2, our point, minus 5.2. We'll have 3.5. What is x1, x2? We have 1 and 2. 1 and 2 minus. So if you did this multiplication, you will get minus 1.5 divided by 2. This is our first point. G1 of x, where x is equal 1, 2. This is how you understand it. Okay, so there is a question about this one. What is, why is log W is cancelled? Okay, so here, because we have B omega 1 is equal B omega 2, which is 0.5. If you add a constant here, if you add this, which should be a constant, then when you calculate G2 of x, you will add the same constant. The same constant in both equations, in both sides of the equation, will not affect which decision you will take. Is that right? It's same as if you add 2 there and you add another 2 is there. It increases both of them. Or if it is minus, it decreases both of them. That's the reason why we cancel it. We don't. What does this point represent? This represent means that what is the posterior or the discriminant function when we have a sample x equal 1 and 2 for g1 of x. Is it right? That will have. So you can think about this way. This is g of x, both of them, the boundary, and my point is here. That's what it represents. Or g2 of x, it might be here. Then we will compare. It's greater than 0 or less than 0. It actually means the contribution of the likelihood when x is equal 1 over 2 for omega 1, for class 1. Similarly, you will have to calculate the things, and we got it like -7. And now you will understand that g1 of x is greater than g2 of x. Therefore, x will be classified in omega 1. That's all what we need for case 2. We will not have any example for case 3 because it's not required. It will not be included in the exam as well. But we'll be focusing on case 1 and case 2. Okay, the thing that I would like to mention before I go to the next slide, which is the last one, which is finding the decision boundary. What does, let me see, there are questions here. Okay, so we have x1. Let me explain both of them, which is 1 and 2. We agree that x is a vector. Let me write it as x. This is a vector of feature 1, x1 equal to 1, and x2 is equal to 2. This could be represented like by nose size, ears, whatever. Is that right? We do have like a normal distribution of case 2 where we have gi, g1 of x, and we have g2 of x. When you think about it in 2 dimension, you might have this one. This is x1, or this is x2, this is g of x. Is that right? So now those 2 points could be here or could be there, and you need to evaluate what is the contribution of that point on g1 of x. It belongs to omega 1 or it belongs to omega 2. Is that right? So what you need to do, you plug in this in the first discriminant function, you plug it in the second discriminant function and find the values. It's not easy to plot it in the 2 dimension, but you can actually plot it in 1 dimension. Assume that we have only 1 dimension. This is x, and we have only 1. This is the point 1. Is that right? We do have a mean. For example, it's like this. We have another one is here. This is our 2 normal distribution. This one is related to g1 of x. This one is related to g2 of x. So now, at this point, what we are calculating -7 and -0.5 is this and this. This is g1 or g2 when x is equal to 1. Here is g1 when x equal to 1. And we compare which one is bigger than the other. The one it lies actually on the normal or the likelihood, which is giving us bigger, then we'll say it's class 1, and the other one is not classified. We will not say it's omega 2. This is how it represents in terms of the values of g1 of x and g2 of x. I hope this helps understanding those 2 points. So the last question is, find the decision boundary for case 1, g1 of x equal to g2 of x, where x is 1 and 2. Okay, you will have to follow this example that I just solved, which going to be omega t, x minus x0. Omega is the rotation of x minus mu1 minus mu2 times the segment's inverse. You do all this process. This will be canceled. This one will be canceled here. because of the equality of the priors, and you will get something like this. Let me see my final answer. You will get the decision boundary. I will post the solution. X2 equal 7 minus 20x1. That is equal to 6. This is my decision boundary, which is a line between omega 1 and omega 2. When you plug x1 and x2, you will find its value. Is that right? Or you can go a little one step before, and it's written as 3 divided by 2, x2 plus 5x1 plus 7 divided by 4 is equal to 0. This is my discriminant function for both of them, g of x. That's the boundary, which is g1 of x minus g2 of x. So now, if you plot this one as x2, which is 2, I guess, and this one is 1, what you will get? Can anyone try? You will get omega 1 or omega 2. We should have the same decision that we did for part 1. Again, this one is x, sorry, this one is 2, this one is 1. It's definitely greater than 0. So we will decide it's omega 1. So in general, when we have g of x is greater than 0, we'll say omega 1, we'll say g of x less than 0. It's just a sign classification, omega 2. Or g1 of x in part 1 as we did, omega 1 omega 2. So the question is, if we have not only 2 classes, now we are studying the easiest way, which we have only omega 1 and omega 2. How about if we have 3, 4, 5 classes? What is the rule to decide which class sample X belongs to? When we have, okay, the posterior, okay, short distance to each class, yes, that's a good one. We will calculate the posterior for each class, then we compare. We calculate the shortest distance to each class, then we compare, taking the minimum distance, and we classify. There are 2 different methods for multi-class classification. One of them is 1 versus all. 1 versus all. For example, and we will talk about this one next time, but to give you like some introduction. 1 versus all means that I will care about omega 1, class 1, and I will treat all the remaining classes as one class, and then classify. Plot my decision boundary between omega 1 and all other classes. We will have a line, for example. Then I will say, let's move forward with omega 2 and treat all of the remaining classes, C minus 1 classes, as one class. Is that right? Then I will have a line. I will have all those lines between classes and classify based on the maximum. The other one is saying that we will have to compare each one with the other, with the neighbor. 1 and 2, 2 and 3, 3 and 4, 4 and 5, all of them. This will have a lot of computation and complexity when we compare all of them. The third method, which is the smartest way, is called linear machine. Linear machine, it's the way that you guys are saying. We calculate the shortest distance to each class and take the largest g1 of x or g2 of x. Or we compare the distances and say the minimum distance of sample to each one of the classes. Or we calculate the posterior. Anyhow, from now on, we will not be dealing with the posterior anymore. We'll be just dealing with the discriminant function and how to find it. So the question is, how do we find this one? We have the probability x of omega I. This is the likelihood. When we write it as log, this one, how do we find this? We haven't talked about this one, is that right? How do we find this? The other one is the log of b omega I. This is easier. This is easy to find because you know some information about the classes, the dataset. You may take a random point and you optimize or do machine learning. But how can we do this? We will learn in the next lecture how can we learn this from the samples itself? And instead of caring about Bx of omega I, we will be caring about different things, which is omega I and the bias, the intercept. Anyhow, we will have only one more slide. You can read it by yourself. We are not very interested in the discrete features, but we'll be considering continuous. Continuous means it's any value between 0 and infinity. Discrete can be 1, 2, 3, 4. Here we have feature x1 can be male or female. X2 can be the hair color. For example, like it's either black, brown, whatever. Those are discrete features. It doesn't take any value between 0, 0.5, 0.5, 5.66. Those are just discrete features. So in discrete features, instead of caring with the integration of the likelihood, we'll be caring with the summation of the likelihood. And this is like an independent, we will call it naive bias classifier. This is the last slide that we had for today. I will stay 6 more minutes. If you have any questions, just let me know. And before we finalize, please solve the problem set. That's very important. This will give you like a hint on, did you understand the lectures? Are you going well with my lectures? If you solve them yourself, I'm sure you will do well in the midterm and the final. They are not difficult, but it needs to care about your calculations. You need to be like familiarized with a lot of linear things, linear algebra. Because in the midterm or in the final, if you have a question saying that find the covariance matrix or find the inverse, then you will say, okay, what is the inverse? You need to memorize all those calculus things. Be ready for that. Do a little bit of practice for solving those, my practice set. I do have 8 problems that I posted. They are covering lecture 2, 3, 4, and 5. Then before the midterm, I will also post so before the midterm, I also will post something about nonlinear discriminant functions, 1 or 2 problems, or 3 problems that will help you with the midterm. Other than that, you should be good. Would we get a linear algebra cheat sheet? For linear algebra, because I don't know how your experience with linear algebra, so I cannot give you anything about linear algebra. But what I can give, I will write the problem, I will solve it myself, and see what you need for solving it. Then I will post my formula sheet for you. Then you will say, okay, I need to add more about linear algebra. I need to add more about distribution. I need to add more about cost function, things that you might think of. Okay, guys. And the other thing that I would like to mention is, please come to your office hour. So today I was like in the Zoom from 4 to 5. If you have any question, if you have anything about the problem set, you want to solve it with me, just come and we'll have a discussion about that. If you want to review some of the slides, we can do it as well. Just use them, and then don't be late for studying to the midterm. Yeah, so that's a good question. Thank you. It's going well. I do have an appointment next week to see if I can remove the cast. If things went very well, I will have to go back to in-person classes. Otherwise, we will continue until the end of the semester. So I'm not put any weight on it. I'm not stepping on it. Just relaxing at home and do my job from home. Yeah, I have received some emails saying that, well, Zoom is Zoom is good because the time is from 6 to 9 and most of you are supposed to be home. But if I am like feeling well, I have to be in person. That's actually the course rule. Yeah, the remote classes is also good for me too, especially with this cold weather, is it right? There are a lot of storms. Okay, just a reminder, next week it's the deadline for lab 1. Are problem set questions similar? Yeah, it will be similar to the midterm. I will not make it difficult for you guys. The midterm will be similar to my examples. It will be similar to the problem set questions. Then in the final, we'll think about it. Yes, it will be like similar to the problem set questions, not identical. I might have something very similar, but it's same trend, same thing, same questions. For example, you have 2 times 2 matrix, find case 1, for example, or like find the decision boundary, classify this point, find the gradient descent for 3 or 2 iterations. It's something like that. It's something from my lecture and the problem set with some changes. Will the midterm be the same for grad? No. It will be different. We will have some common problems for graduate and undergrad students, but graduate students need to pay a little bit of pain. Is that right? Yeah, we will have some different questions for graduate students. Yes, final will be different for sure, but midterm I might have 1 question is different, and then 3 questions will be same. In the midterm, we will be having 4 problems for 2 hours. Each problem will have 30 minutes. 1 problem will be different from graduate students and undergrad students. I will mention that in my announcement. So when you do the test, I will say problem 1 in a bold writing is graduate students. That one is undergrad students. They will have the same weight, but for undergrad it will be easier. For graduate, it will be a little bit tough. 1 problem only, huh? And in the final, we will have different rules for the final. Okay, those who are still like concerned about the heavy math, I think that's normal. I believe that even for undergrad students, you are now almost to be engineer. And this course will take you actually, if you continue with masters or industry or whatever, you need to understand those deep math. In the exam, it will not ask you to drive this or drive, it's all like problem set, solving numbers, is that right? But after the midterm, we will not have that heavy math. It will be slightly same as any other course. We will be focusing more on application, not on deep math. Okay, guys, so I will have to leave because I don't receive any question from you. And we will